Hello, chemistry students. One of the most important things we talked about this year in all of chemistry was bonding and how the periodic table worked. Now, I'm just going to briefly review, we're talking a run through the entire year's worth of ideas in just this 10-minute lecture. Obviously, I'm not going to hit everything, but this stuff is foundational to going into the exam. I remember the first year I taught this, I had just some kids who didn't care, and they were clueless when they went into the exam on bonding. Absolutely clueless. It broke my heart. They were double bonding things that were never meant to be double bond, and putting things together that made a chemist's soul cringe. I'm pretty sure the ghost of, some famous chemist will haunt them forever for making such egregious mistakes in high school. Probably not. Here's our periodic table. Now, we know these by section. For instance, these are the alkali metals, the alkaline metals. These are the transition metals. Hey, they're even labeled. These are the semi-metals or metalloids. These are all nonmetals, and these are noble gases. These specific nonmetals are known as halogens. And they even have really cool names. Post-transition metal. I haven't seen that in a while. That's a kind of a rare thing to call them. Now, the periodic table was very wisely arranged by a Russian dude who I think his name was Moseley and Dmitry Mendeleev. Very wisely arranged based on the valence electron count. What's the valence electron? Valence electrons are the outer electrons in every atom. So this column here has one valence electron. This column here has two valence electrons. This is a mess. 3, 4, 5, 6, 7, 8. Now remember, 8's what they want to get. Unless you're helium, then you have 2 and you're fine. But 8's what you want to get. And if you are a lithium, you're so far away from 8. It's easier to get rid of the one you have, and you go back to actually having a full shell. I'll explain that in just a minute. Alright, I'm back after that Skype call. Now, here's why, as we were talking about, it works when you lose an electron as a metal. So here's sodium, right? I'm going to type in sodium. Na, or sodium. First thing that comes up is a joke. Well, that's not good. So here is Na. And here we see Bohr's model of the atom, which is very useful, even though Bohr did admittedly get some things wrong. And quantum model works better, but Bohr's model is great in this case. You see this shell? 1, 2, 3, 4, 5, 6, 7, 8 electrons in shell 2, 1 in shell 3. Shell 3 is technically its valence shell because it's the outside one. Sodium has 1 electron in its valence shell. Sodium's not very happy about that electron. So if it gets rid of that electron, now it goes to this shell and has 8. And now it's pretty happy. Same thing with magnesium. Magnesium has 2 valence electrons in its outer shell. If it gets rid of 2, hey, it's doing pretty good. You get rid of these 2, now it has 8 on its valence shell. It's all good. Now, with that being considered, if a metal bonds with a nonmetal, it's going to be an ionic bond because the metal's going to give away its electrons instead of sharing. But if a nonmetal can't find a metal to bond with, nonmetals are going to bind with each other. And when nonmetals combine with each other, they make covalent bonds. And covalent bonds are different because whereas ionic bonds are electrons stolen, covalent bonds are electrons shared. So if fluorine bonds with like oxygen, it turns out that oxygen's not going to want to give up its valence shell. Fluorine's not going to want to give up its valence shell. They're going to end up kind of sharing electrons to get what they need. And these are the two most frequent kinds of bonds. The only ones left are metallic bonds, which happen around here, and they're really poorly understood, and kind of strangely complex. And so anyway, that's where most of the bonding begins. Now I'm gonna add one more in here towards the end. Let's see. I'll add one more in and give you an example of an ionic bond. But anyway, I came up with a short PowerPoint on bonding. Maybe you can take a look and work with me, write these things down. So, C2H6. Well, carbon has 4 valence electrons. It needs 1, 2, 3, 4 bonds in order to make carbon work. So we're going to set up these carbons next to each other, and each carbon needs 4 bonds. Well, they already have 1 bond with each other, so here's 4 bonds for this carbon, 4 bonds for that carbon. How many hydrogen do we have? 1, 2, 3, 4, 5, 6. Hey, C2H6, also known as ethane, works out chemically, and we're all good. Here's another one, NO3H3. I don't know what that makes, what its technical name is, but let's see if it's creatable. So we have nitrogen. Nitrogen has 1, 2, 3, 4, 5 valence electrons, so it needs 1, 2, 3. Okay, and so we'll make one. Let's go 2, 3. Hey, now oxygen needs 2 bonds. We'll look back here. Oxygen needs 1, 2, and oxygen only has 1 right now. But fortunately, we have enough hydrogens to give everybody a every oxygen a bond. So now oxygen is 2 like it needs. Each oxygen is 2, and the nitrogen is 3. This is a complete molecule. We could also design this any number of ways. This is an isotope here. We could potentially string these guys together like that and create it a little bit differently. And sorry, did I say isotope? I meant isomer. Oh boy, I'm getting my isos mixed up today. Isotope varies in its number of neutrons. Isomer varies in its construction. So, anyways, here's another one. P2F2H4. So P right here needs 1, 2, 3 bonds. F needs just 1. Hydrogen needs just 1. And so let's set it up here. You can really set this up a couple of different ways. I'm going to go like this. I like symmetry. Let's see. Let's make sure we did this right. We'll find out. Phosphorus needs 1, 2, 3 bonds. It has 1, 2, 3, 4. Huh. Will this work? The answer is no. This is not a buildable molecule. This one here. It is not possible to build this thing. It would be possible if we had H2 and we were able to just scribble these guys out and have that. I mean, that's totally possible. But H4 as it stands is impossible, and I've seen this. You guys will do this on the exam, okay? And it will break my heart. You guys will do this. Ah, perfect. I fixed it. Don't double bond a hydrogen or have more than one bond to a hydrogen. Please don't. It will cause me great sorrow. Let's go on to the next slide. This one's going to be ionic because it's not shared, it's stolen. And so you have sodium here. Let's see. Sodium here has just one valence electron. Let's draw that valence electron. Chlorine has 7. Neither one of them's happy right now, but if they connect with each other... Now chlorine has 8. Sodium has 0, but remember how I told you that if it gets rid of its valence shell, the shell underneath has 8. So technically, sodium has 8 too, and they're all happy. And this is ionic instead of covalent. Constructed a little bit differently, where we actually see where the electrons are. We can do this with covalent bonds. We can do Lewis dot structure, where you have little dots surrounding the atoms, but we're not going to do that one. Here's the last one, NH4. Alright, and you're thinking, oh, this is kind of easy. Hey, done. Come on, Mr. Ripples. Why is this the last one? But again, nitrogen needs how many bonds? 1, 2, 3. This, NH4, does not exist. You cannot have NH4. You can have NH4 positive, and that happens when the nitrogen is missing an electron, so it comes in with 4 electrons instead of 5, and needs 4 bonds. NH4 is, let me show you on Google. NH4 is called ammonium, and you see here that it's NH4 positive. You can't just have NH4. And so, anyway, those are some of the basics of bonding. I just want you guys to really grasp the ideas behind all of this. And if you have any questions, please let me know. And I hope you have a really good day. All right? See ya.